So I'm going to give you the matrix so you can spot check that. But we talked through this just on Monday. You take the delta U dot equation and the W dot equation, set it equal to 0. In fact, we worked all that out. We wrote it out, but make sure you show these equations. Even if you just copy them from the lecture on Monday or from your notes or from the board. And remember, you have to do Q is delta theta dot, so you put everything in terms of delta U and delta theta. And you get two equations, you Laplace them. Just like the steps we did in class for the other mode. And you should get this matrix. I've posted the lecture on YouTube from last Monday if you have to go back and refer to that to grab the equations, but you should end up with that. And then you take the determinant, which is this thing times that minus this stuff times that. So make sure you show this step, show the Laplace step, and then show that you took the determinant. Now, most often, I'll give you a minute to copy this down, and then I'm going to futz around with it. Yeah. For what? For this? Yeah. Oh, yeah. So they're saying that the control is just x sub c. Yeah, that's fine. Yeah. Yeah. The delta what? I'm not following. Delta E. This one here? Oh, yeah. Okay, I see. Like that. Yeah, sorry, I just left it off. Well, no, the control is x delta E times delta E. So that's what we're calling x sub c. Right, so this is the drag due to the elevator, and this is the lift due to the elevator, is really what it is. But I'm okay with you just put, because initially in the equations they put x sub c and z sub c that contain both of those. Yeah. Is that okay? Okay. Now, I didn't ask you to do this on your homework, but typically this is simplified a little further where we'll say we're in the level flight where theta 0 is 0. Yeah, I just want to make sure I got my cosines and sines right here. Yeah, so if you do that, then this becomes 1, and this becomes 0. And so that knocks out those terms. And then often the ZQ term is small, because this is the lift due to pitch rate. And so you can knock that out. That's small compared to this big velocity here, U0. You can simplify to get a much simpler determinant if you do that. And so the simplified determinant is should be an S here. And so that's a much simpler second order polynomial that often we'll use as the approximation. But I just wanted you to stop at this point so you see the process that you get to. So if you assume these, then you get a much simpler second order polynomial, and it's easy to take the roots using the quadratic formula. All right, and then I want to show you the numbers plugged in for the second problem, because there's a lot of numbers, and that way you can spot check what you did. So we did what I'm listing here, the short period mode. We did the 2 by 2 matrix, and then we took the determinant. So this we had from the class on Monday, is this determinant here. And when you substitute in the numbers from the table, that's what I'm going to show you down here, is this whole thing here. So I'm going to give you a minute so that you can spot check your numbers, and I'm going to scroll down, because this is the final result down here. So if you have all these numbers right, then you know you did this right, and you don't need to spot check it. But I want to help you troubleshoot if you need to look through this. And you guys on Zoom, I have no problem if you do a screenshot of this, and if you guys want, because there's a lot of stuff here to write down, if you guys wanted to capture that in here, yeah. Yeah, I'll try to get it converted. I have to pull it into Camtasia and then edit it down and then upload it, so it takes a while, but I'll try to do that. So make sure you show this step where you plug in the numbers, and you're really just plugging in all the numbers into this, but obviously there's a lot of numbers. So you should get this polynomial here, and then if you divide through by the 0.9934, because you're going to set this to 0, you could factor it into these roots here. So here's the answer you should be getting. So am I giving you guys enough that you can work through this on your own now? Hopefully. It takes a little bit of time. Just make sure that you get the numbers put in at the correct place. And I gave you that one typo last time, right? It was 10 to the 5th instead of 10 to the 4th. All right, any other questions? This one here, or the one in the previous? Just multiply these two and collect the s to the third terms, s squared terms. Then that's it. All right, the second thing we need to talk about is the final exam. It's Wednesday from 9 to 10:50 a.m. It's multiple choice. And it's comprehensive. So it covers the whole semester, which, since it's multiple choice, there will be short answer kind of stuff. It will be concept questions, but there may be a few calculations. I'll give you a formula sheet with the formulas if you need them for the calculation. So have a calculator and be ready to calculate. But some of it is just pick the correct answer. It's multiple choice. You're given some information and then you're asked a question. So make sure you go back and study all the quizzes that we've had during the semester. Look through the homework, and especially focus on the kind of stuff I do on the quizzes are definitions, right? Concepts, terms, what do the symbols mean? What are different, like what's the neutral point, definitions and things like that. I'm still deciding on how I'm going to administer this. Typically, it's done as a Scantron final, where you come in and you fill out the Scantrons with the little bubbles. I'm trying to decide. Last semester in this class, we did it online because that's what we were doing. Everybody was remote. Kind of worked, but it wasn't ideal because the way that I have to set it up is that you can't backtrack. I mean, I could let you backtrack, but then it just doesn't work. If you guys are remote and you try to backtrack and I do it in a random order, and it makes it harder, I think, to take the test. A lot of students did it and they did okay, but the online experience was frustrating. So I'm trying to figure out how to do that. So give me a couple days and I'll shoot out an email to the class to tell you how I'm going to do that. Either way, it's just about the same for me to grade. I want to make sure that you guys have the best opportunity to do as well as you can on the final. All right, any questions about that? Again, it's not long problems, it's more definitions, concepts, simple calculations that we've done through the semester. All right, I want to wrap up the mode analysis that we started last time by looking at the roots of the BizJet and talk about, well, how do we figure out whether they're good or not? So we talked about a first order mode. Last time, which meant that we had just a real root A. And that turns into e to the AT, and we found out that people talk about this by defining this time constant, tau, that's -1/A. And it has to do with the time that it takes to damp to 1/E to 0.368. So the bigger the time constant, the longer that it takes to damp, and the more lightly damped it is. So for our example, for our BizJet, we had a root, a roll mode root. This was one of our first order modes of 0.5003. So you do the lateral directional full 4x4 matrix, you find the roots of that, and one of the roots we got was this with a minus sign. So that means the time constant for the roll mode is minus 1 over minus 0.5003. And so that's 2.0. So it takes 2 seconds to damp to 1 over E in the roll mode. And that tells us how well damped the roll mode is. And so then you go and you look up specs. And the ones that are most commonly applied to these are the military specs for the roll mode. And for the roll mode time constant, these things say you want a roll mode less than 1.4 for what's called level 1 flying qualities, and it needs to be less than 3 for level 2. And these are just different levels of how well the airplane behaves. And the military specs are applied to general aviation aircraft, but they're usually relaxed because the military wants their airplanes to be super responsive and well damped, whereas for business jets, it's usually relaxed. And so what we do is we look at this time constant and we compare it to the specs, and we would say, well, this meets level 2. Because it's 2 is less than 3.0. And for a biz jet, that's just fine. So that's the kind of analysis you do. Where did these numbers come from? They did lots and lots of pilot experience and evaluations to establish what are good roll mode time constants and what are not. So all this stuff comes from pilots giving feedback and say, yeah, I really like flying this airplane because the roll mode is like this or that. So thousands and thousands and hundreds of thousands of pilot hours ever since the first flight back in 1907. Gosh, I should know that. 324. You guys know that? When was it? December 3rd? Right, brother? Huh? December 17th, 1903. Good for you. Extra credit, yeah. Maybe that'll be a question on the final. That would be unfair, right? Now I'm trying to remember the other date that will live in infamy. Do you know what that is? Pearl Harbor Day, December 7th, 1941. Yeah. There's a cool air show if you ever get a chance to see it called Tora, 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 where they reenact that. And it's been done here in Wichita multiple times, out at McConnell and at Jabara. Okay, all back to this. Okay, so then, let's see. That was the roll mode. How about the spiral mode? How do you analyze that? So the way the spiral mode is analyzed is what's something called the time to double amplitude. And the specs for this say that it has to be greater than 12 seconds. You're saying, well, what does double amplitude mean? It means that this can actually be unstable and be okay, as long as it doesn't take, or it takes longer than a certain amount of time to double amplitude. So if it starts at, the exponent starts out at 1 and it actually diverges, but the time to double amplitude takes longer than a certain amount of time, which means the pilot has time to react to the unstable mode. And so the time to double amplitude is calculated with the root using this formula. So you plug in the A, that's the root from the dynamics, and then you calculate that, and then it has to be greater than 12 seconds. So how about the BizJet? The root for the spiral mode for the BizJet was minus 0.001. So if you stick that up in here, you get a negative time to double amplitude. What does that mean? It means this is stable, so it does not double amplitude at all, so it automatically satisfies. Because this is saying how unstable it can be, so if it's stable, it's got to be better than unstable. That's the normal analysis that's done. And then the Dutch roll is analyzed by looking at the damping ratio and the natural frequency of that mode. So I'll show you how you calculate that from the roots. So the Dutch roll specs say that the damping ratio has to be more damp than 0.052. And this is for level 1. And there's a whole bunch of behind the scenes stuff that I'm leaving out. This is kind of the basics. There's a whole chapter in this, in the textbook that we use for 714 that covers all of the various different contingencies and aircraft types. But what I'm showing you here is for Part 23 aircraft, which are civilian aviation aircraft. And the damping, the natural frequency has to be greater than 1.0 radians per second. So those are the specs. Zeta or C, it's a squiggle. That's as best I can do. If you look it up, I mean, and the fonts have it actually written really well. I mean, sometimes you see it like this, something like that. And most people call it squiggly. Yeah, it's the damping ratio. So for the BizJet, these are the roots that we got, complex conjugate pair. And so if you're given the roots, then you have to turn them back into the second order polynomial, because we want s squared plus something times s plus something, and then we set that equal to 0 to get those roots. So how do you get back to this stuff here? In fact, we're going to put this in the form of the standard form so that we can get these. So let me write that instead. Remember that standard second order form from the Laplace tables? That's what it is. And so we have to multiply these things together. Right, so there's the two roots. And why do we flip the sign on it? It's because a root is a value of s, that if we stick it in for s, it makes it 0, right? So this is the opposite sign of the thing that's the actual root, because that's what a root is. It's a value of s that makes this 0. And so you have to multiply all that out. And it turns out that once you've done this, you realize that it's not as hard as it looks. So you get S times S is S squared. And then you get an S times that thing and an S times this thing, right? But they're complex conjugates, so the plus and the minus cancel each other out, and you get 2 of this thing. Everybody see that? So this S times this is the 0.0653 plus that, and this S times this, you get the 0.0653, so that's why we have 2 of them. But then the S times the plus and the minus cancel each other out, so those are gone. And then if you multiply, the last factor we have to do is this times this. And again, you get cancellation. You're going to get this times this, so you get that squared. And you get this times this, so you get that squared. And then the I times I gives you a -1 that cancels out with a minus. So you get this thing squared plus this thing squared. And then the cross products of the minus times this and the plus times this cancel out. Do you follow all that? You just take these 2 numbers and multiply them together. The cross products cancel each other out, and you get this thing squared plus this thing squared. Where in math do you guys talk about complex numbers and that stuff? Like you talk about complex numbers in high school, right? If you take pre-calc and algebra, I guess. Yeah. So you almost have to just do it yourself and multiply it out, that times that times that times that, and then you realize you get this. But this is what gives us the natural frequency squared, and then this is the damping ratio times the natural frequency, because it's 2 times that. And so you can back out the natural frequency and the damping ratio to compare to the specs. And so for this, this is what we get from this thing down here. And so then you look at the specs. And we look at the natural frequency and we go, it meets level 1. So you put a check mark. And then you look at the damping ratio and we go, our damping ratio is not high enough. So it's actually underdamped. And this is the reason why people add a yaw damper to add more artificial damping using an output feedback controller, and you'll learn about that in 607 at some point. And that's normal. A lot of airplanes will have a yaw damper because the aerodynamics drive the root to not be well damped enough, and so you just fix it up. How are we doing on time? 11 o'clock. I know most of the people are, I mean, quite a few people in this class are probably not going to go into flight dynamics or controls. Maybe you'll be in structures or aerodynamics, but you'll be at companies where they'll start talking about these different modes. And if you're knowledgeable about them and you can sound intelligent, then maybe you'll get a raise and you can thank me for it. Right. Who knows? And I've told you my deal, right? The deal is that if anybody in here becomes rich enough to buy and own their own biz jet, you have to give me a ride. So far, nobody's done that. Although they have a lot of successful graduates that have done cool stuff. So the last 2 are the longitudinal modes. And both of these are complex conjugates, so you have to use the same deal that we did with the Dutch roll. The short period, the mil spec for that says the damping ratio needs to be within this range here to be level 1. And then the natural frequency has to be within this mode or this range. And then for the fugoid, all you do is look at the damping ratio, and it needs to be somewhat damped. That's not very strict condition, but the damping ratio has to be bigger than 0.04. And remember, this is really low frequency. So typically, the low frequency allows the pilot to compensate for the damping not being great. So if we take the BizJet and we take the short period mode, and then we look at the fugoid mode, and how do we identify these? Remember, the one with the high frequency is the short period, because it's the short period. And then the long period fugoid mode is more lightly damped with the lower frequency, and that's the fugoid. So this is short period. And I emphasize that because that could be on the final. That's a hint. Be able to identify the different modes, the Dutch roll, the spiral, the roll, the fugoid, and the short period based on the rules that I've showed you in class. So this thing, if you do the analysis, we take the plus and minus roots and do all the multiplication out and identify, go through that same algebra process. You find out that the natural frequency of the short period is 2.83, and the damping ratio is 0.353. So what do we think about that? We look at this and we compare it to that, and we go, that looks good. That's level 1. How about the damping ratio, the natural frequency? Looks like it's a little bit high. So this would actually be level 2. So either you fix up the airplane to get that frequency down, and that's where those approximations come in, is because you can look and see, well, what parameters do you need to change to fix this up? We don't have the time to go through all of that in this class, but that would be the process, is you change the airplane, or you live with the mode that's not quite so good, or you add artificial damping. And then for the fugoid, we get a natural frequency of 0.0921 and a damping ratio of 0.047. And then we look at the specs and we see, well, all we really need to do is meet the damping ratio, because there are no specs for the natural frequency. And 0.04, this is definitely bigger than 0.04, so this meets level 1. I'm not finding my handout or what I wanted to show you about wind tunnels. Where is my handout? Well, we might just talk through it. So the idea is, where do you get a lot of the parameters that show up in the aerodynamic models? We've talked through in this class how you would calculate them using the charts for the airfoils for the wing, and then we build up the wing and we get like CL alpha, the lift curve slope for the wing, all of that. But once you've done the calculations, then you want experimental validation of the aerodynamic numbers. These are the numbers that go into like those ZUs and X delta E's and all those parameters that show up in the dynamics. And so the next step, once you've done the preliminary design and calculations, like we've done in this class for our airplane, then you build a wind tunnel model and test it in wind tunnels. Makes sense. And then you could do what we did. We imported it into X-Plane and essentially flight tested it in simulation. So that's typically done to test out the dynamics. And a flight simulator, they would bring pilots in and run their simulated model to see how well the airplane flies. And then eventually you build a prototype and test it. And that's in order of increasing costs. So the prelim design calculations, you hire some people and they sit down with computers and books and charts and they calculate it. So that's pretty cheap. And then you build a wind tunnel model. And you test it. And that costs more money because you actually have to build a model and put it in the wind tunnel. And then you build a prototype. And then you fly it. And that's more money. In senior design, 528, 628, you do all of this. You'll do a preliminary design for a radio control airplane. And you do that the first semester and then early into your second semester. Then you'll build a wind tunnel model. You actually typically build actually a prototype of your airplane because you're just building a radio control, and then you put it in a wind tunnel and test it to validate your design. And then you will actually fly that in a competition and a fly-off. A bunch of the senior design groups are flying this Saturday. Have you heard about that? Through experimental methods. They're participating in a bronze propeller competition. Maybe some of you know about that. It's at the Heskett Center starting at 11 o'clock and it goes through till 4. And they're upstairs on the second floor. They're flying indoors this year, just because the schedule's kind of compressed and they don't, Dr. Miller didn't want to dodge weather and trying to get everything in with our shortened semester. So if you want to see what they're doing, stop by the Heskett Center on Saturday and you can watch them fly. The wind tunnel testing, you can measure lift, drag, and pitching moment of your wind tunnel model, which essentially gives you CL, CD, and CM. And you'll do this with alpha sweeps and at different elevator positions. And so if you do that, then you get the stuff that goes into our aerodynamic models, like CL0, CL alpha, and CL delta E, because this is just the slope of the CL versus alpha plot, and this is the slope of the CL versus delta E plot. And you get that for lift, drag, and pitching moment. So these are the parameters that go into those aerodynamic models. The big one that you'll get from wind tunnel model in wind tunnel testing when you do your senior design is you want to look at this plot really carefully, the CM versus alpha, because that's your pitch stability. And you want to make sure you got a negative slope on that plot when you test your wind tunnel model. There's a story that Dr. Miller tells about a senior design group a long time ago, years ago. Have I talked about it? Yeah, he's probably, yeah, I'm sure he tells it to every senior design class. That there was a group that went into the wind tunnel and they came out with a plot, and it kind of went like this, but then it went up like that, and then it kind of went like that because they went from stall to stall. And so this is CM versus alpha. And they looked at it, and they had to fly tomorrow. The next day was the day that they needed to fly, an opportunity to fly. And the guy that did their stability and control said it's unstable, and the rest of the group said, doesn't matter, we got to fly. And it didn't turn out well. So yeah, I'm sure he'll tell you that story. And then you do the same thing, lateral directional, right? We want to be able to pitch, to predict rolling moment, pitching moment, rolling moment, yawing moment, and side force. And so you can measure those values versus beta, rudder, and aileron so that you can get all of the derivatives that go into that model. So I'm going to measure CY, side force, rolling moment, and yawing moment versus a beta sweep. And then you do that with the rudder set at different values and the aileron. And so then you can get the model that goes into the math model for side force. And the same thing for rolling moment. Oh, yes, thanks. Should be over here. There we go. This is delta A. We're still good on time. So then you can get these important parameters. The key ones here are the CL beta and CN beta. We know we want CN beta to be greater than 0 and this to be less than 0. This yaws into the side slip and rolls away from the side slip for stability. But this will also tell you whether you have enough aileron power. And in fact, these things go directly into the roll mode time constant along with the stability. And so these are the kind of things that you check to make sure you can roll or bank the aircraft fast enough. With wind tunnel tests, just like progressing through the different stages of your design on your aircraft, if you have a low speed test, which you will be doing in senior design, that's cheap to do. You can do that with a small model in the 3x4, the smaller wind tunnel that we have. Or if that breaks, you have to go to the beach wind tunnel, but it's still pretty cheap. But then if you want to fly, let's say, near Mach 1, so let's say you want to fly at Mach 0.83, you're developing a jet that's a biz jet where you want to fly fast, then you got to go into a transonic wind tunnel that can fly faster, and that costs more money. It's just life. And then if you say, oh no, I want my airplane to go supersonic, I'm going to make a supersonic biz jet, which a lot of companies are working on now. Then you need to go into a supersonic wind tunnel, which costs more money. And then if you're really serious about it, you want to do a full-scaled wind tunnel test, which is typically only done for military aircraft because it costs a lot of money. You go into a giant wind tunnel and fly your airplane in the wind tunnel full scale, and it costs a lot more money. And then typically, for military aircraft, they will go into what's called a spin tunnel, where it's a wind tunnel where the air blows up from below, up through a tower, and a guy stands at the top of the tower with the wind blowing up with a model and throws it like a frisbee out into the air and starts it spinning, and then they can measure how the airplane spins, what are its spin modes, so that they can validate other parameters that I haven't listed here, like, for example, CLP and CLR. These are the roll rate and yaw rate derivatives. And so they can get those out of a rotary balance tunnel and a spin tunnel because they want to make sure that if that aircraft spins, that they can recover from the spin while it's spinning. And that costs even more money. And the same stuff is done in flight test. Once you build the prototype, you'll flight test low speed, you'll do high speed tests, supersonic tests, obviously all that's full scale, and then you'll check out the spin modes of the airplane. With a military aircraft, they will put what's called a spin chute. It's a parachute that can deploy from the back of the airplane. And if it gets into a spin that it can't recover from, that chute is deployed and it slows down the spinning and allows the airplane to recover nose down. Then they detach the chute and then it can recover from the spin. So these are the different processes related to the aerodynamics and flight dynamics model. And of course, you're being exposed to, well, what do you do in structures? How do you test wing boxes and all that to make sure the structures can handle the loads and things like that? All right, that's it for today. Finish your homework, turn it in on Friday. There's no class on Friday, you guys know that. It's the study day. And then look for information about the final on Blackboard. I will send out an email and put an announcement there as well. Let's see if I've missed some questions on chat. Looks like I missed a question. It wasn't T sub 25, it was T sub 2S. Sorry about that. 1941, somebody got the date right for Pearl Harbor. All right, hopefully it's been an okay semester, even with all of the stuff going on. Look forward to seeing you guys around next semester in the fall.